So I had said in the solutions to one of the potential problems, I think it was problem number 4, that it would be interesting and kind of instructive to show that doing the problem sort of stupid way um, would it would just be instructive to show that you get the same answer. The problem was, I'm going to draw it sideways so we can be in cylindrical coordinates. You've got a hemispherical shell of radius r, a hemispherical surface, and you've got some kind of potential, a uniform potential E pointing in that direction. They wanted to know what is the flux through this area of the hemisphere. And the point of the problem was to realize that the flux through that hemispherical surface has got to be the same as the flux through um, the, the base. So the answer is just E times pi r squared. Um, it's actually extremely straightforward. Um, if we use the definition of the flux, that the flux is equal to integral of E dot dA, and imagine integrating that electric field over the surface of the sphere, that's actually complicated because the dot product of the electric field and the normal to the surface is not constant. But if we were to do that, we should get the same answer. We should get that the flux is just E times pi r squared. After all, if our argument is that those two things are the same, we should get the same answer if we were to actually do it. So I thought I would try to just actually do that integral and see if I can do it and get it right. I haven't tried this yet, so I might screw it up, and maybe I'll start over, or maybe I'll start the whole video so you won't know that I screwed it up. But if we just imagine now that we're in cylindrical coordinates, so this is our z-axis, and this is our hemisphere that we've placed in the xy plane. The first thing we need to understand is what is the differential element of area on a surface. The magnitude of that dA is just the surface area that we get here when we change. Did I say cylindrical coordinates? We're not going to do this in cylindrical coordinates. We're going to do this in spherical coordinates. The geometry of the surface lends itself to spherical coordinates. The geometry of the field lends itself to cylindrical coordinates, right? Because the electric field points in the z hat direction. E equals E0 z hat, we can write. But the thing we're integrating over is the geometry of the hemisphere. So let's do this in spherical coordinates. In which case, the area of this little bit of little slice we get when we change d theta and d phi. If you remember, if you think back to the volume element in spherical coordinates, remember that that volume element has sides dr and then r d theta, and then r sine theta d phi. The area element is just going to be that without the dr, because we're not changing, we don't change the radial, there's no differential element radially if we're just using dA. So dA is just going to be equal to r squared sine theta d theta d phi. So that's the element of area on the surface of our sphere. So the flux is going to be equal to the integral of E dot dA, which is going to be equal to the integral of E times r squared sine theta d theta d phi. But then there's going to be an element that has to deal with this dot product. E and dA are not always perpendicular to one another. If we simplify this drawing to just look at a slice of it, at any point in the sphere, dA, the normal to the surface, is just in the r hat direction, while E is in the z direction. The angle between that surface normal and the z direction is just the same as our polar angle in spherical coordinates, our angle theta. So the dot product is just going to be E dot dA, which is going to be equal to E dA cosine theta, right? The dot product is 1 up here, where the normal and the field are in the same direction, and it's 0 down here, where the normal and the field are in opposite directions. So this is going to be equal to the integral of E dA cosine theta. So our integral is going to be equal to E times r squared sine squared theta d phi cosine theta. What are our limits of integration? Our limits of integration have to capture the hemisphere. So to capture a hemisphere in spherical coordinates, phi is going to go from 0 to 2 pi, and theta is just going to go from 0 to pi over 2, right? We only need to integrate theta down to 90 degrees and phi all the way around the hemisphere. So what have we got? E is constant, that can come out. R is constant on the surface of the sphere, that can come out. So we've just got E times r squared times the integral of d phi from 0 to 2 pi times the integral of sine theta cos theta d theta from 0 to pi over 2. This is just going to give us a 2 pi, so I've got 2 pi e r squared times this integral from 0 to 2 pi of sine theta cosine theta d theta. So all we have to do is to do this integral. The easiest way to do this integral is we happen to remember the double angle formulas. This integral is actually equal to minus a half cosine squared of theta. And we evaluate that from 0 to pi over 2. So we've got minus a half, that cancels out 2. We've got minus pi r squared e times cosine squared theta evaluated at pi over 2. Which is 1. No, that doesn't work. Oh, pi over 2, which is 0 minus cosine squared theta evaluated at 0, which is 1. So that's minus 1 minus, that gives us pi r squared e, okay, which is exactly what we got by assuming the easy method of just finding the electric field over the flat surface that defines the bottom of the hemisphere. Okay, so the flux through this hemisphere is the same as the flux through this flat surface. This is a lot harder to do than just pi r squared times the area, but it has to be true that if you integrate the electric field over this surface, the flux, which depends only on the perpendicular component, the component of the field that passes through that field, that you will get the same answer. So I thought it would be nice to try that, just to show that the answer you get is in fact the same.